Good. We started with torsion in the last class, and we gave a slight hint of how the behavior of torsional members have, behavior of torsional member under any torsional load, behavior of SAPs, and also we learned a few, assumptions or a few simplifications that we do while solving torsional members, right? So I will just directly go to the assumptions that we make or the simplifications that we make. One of the simplification is, if you see this figure, if you have a torsional member, right, and if you give a twist to the shaft or the torsional member, the straight lines that were horizontal in the beginning will not remain straight line. It will remain straight line, but not remain horizontal. It will become an inclined straight line. Okay, that's one. The circular section, the circular cross sections do not distort. They remain circular before and after, your twist. They also do not expand in length or contract in length. Neither of those two happen. These are all because of symmetry. As I said last class, these are all because of asymmetric cases. These are all because of symmetry that it happens. Example, if a line which is perpendicular, within the cross section doesn't remain perpendicular after twist, let's say they become like this, then all lines will similarly behave, right? There won't be any difference because this is an isotropic member and it's symmetric, right? So there is no importance of any particular material property at any particular direction. There is no directional importance or directional dependence. So therefore this line, if a perpendicular line doesn't remain perpendicular, then all the perpendicular lines will not remain perpendicular, and therefore you will see there's a void that will create, right? And which is not proper, or this is not according to the continuum. So the continuum has to maintain, and therefore all perpendicular lines will remain perpendicular, but they will rotate. Definitely they will rotate because of the twist. Similarly, if a straight line doesn't remain a straight line, it gets twisted, right, this way, then all the straight lines are supposed to get twisted. Okay, and that cannot happen, because if all the lines get twisted, then there will be overlap of lines, and that's not going to happen, because all the lines should remain within the plane, within this material plane, and therefore there cannot be any twist. So the straight lines will remain straight lines within the cross section. Okay, but we also, these are not true when you have a non-circular section, because when you have a non-circular section, definitely there are there are directional dependence. For example, there are principal directions, there are principal axes, right? You have already done those things in engineering mechanics, I suppose. There are axes about which there is symmetry, right? And there are axes about which there is no symmetry. So there are lines which are important and which carry more importance than other lines. Therefore, in members that are not circular, the twist will deform, or twist will, elongate or constrain or compress lines according to its the loading diagram or loading direction or the twist direction. Therefore, we get something called warping in this kind of materials, which is not visible or which doesn't happen in case of circular members, circular crosses. And then we try to define what is an angle of twist. The angle of twist we will define today again. Suppose this is before twist. This diagram is before twist, and this diagram is after twist. Okay. So before twist, you make a mesh of of circular and horizontal lines, and you see there is a line which is almost a rectangular section, right? Now, after twist, if I give a twist in this direction, all these lines, so this point, this wall where it is fixed, will not have any deformation, any twist, right? Because that is fixed. And according to the fixity, it will not have any deformation. But this point, this side is free, right? So when you twist this is supposed to move according to the twist. So these lines will move. So the lines will be as it is in the beginning at the wall point, and then at the free end it will become a little bit twisted, but all of these lines will remain parallel to each other. Okay, All right. So this from a rectangle, it will become a parallelepiped. And therefore, what is the strain? The strain is change in the angle, right? So there was a right angle here. Now it is no more a right angle. Okay, so this change in the angle is your strain. That's called shear strain. We already know that. That is a shear strain. Now, how do we calculate this shear strain? Shear strain. So to calculate that shear strain, we have to, calculate angle of twist. How do you get angle of twist? So now you see that every cross section, any cross section that you take from here, the points that were initially right angle like this, xy axis, they will no longer remain right angle. They will remain right angle, but they will just rotate, right? Like this. So if I take a cross section at B, and this is the circle at the B, okay, and this was QP was your initial orthogonal lines, which will now QP, which were your initial orthogonal lines, now rotate by Q dash and P dash. Now, if you take another coordinate, another section at A, which is far away from the boundary, you get another curve where N and M were orthogonal to each other. Now they rotated by N dash and M dash, right? Rotated to M dash and N dash. And this rotation is obviously much larger than this rotation, and the rotation will be 0 at the boundary, right? Therefore, you see that there is this change which is increasing with the x value. All right. So that angle, this angle that is formed subtended in the center, which is same as the rotation angle here, remember, if for the cross section, is called angle of twist, phi of x. Okay. So this n dash, m dash forms a rotational angle, which is called angle of twist. So let's say this is called phi b and delta phi b and delta phi a. So the change in length, not change in length, the shift from n to n dash is, or shift from m to m dash, they're going to be same because it's symmetric, is r d phi a. R is the radius of the cross section. And similarly, PP dash and QQ dash is R d phi BB, where R is again radius of the cross section. So we have calculated how much shift has happened. So we have already got how much shift has happened here. So if this was the line, initial line, and this is your after twist line, same line, then this one is calculated now. This shift is calculated by these values, right? So this is because of this cross section. This is because in this cross section. Okay. So those two values are calculated. Now, how do we use that value? Okay. Now, shear strain, we know that this is a block, rectangular block, and if it undergoes some shear, it will become like this. Okay. And the shear strain is the change in this angle, right? Now, this change in the angle, if you see, will be maximum at the upper surface of the member of the shaft. It will not be in the inner member. It will be at the maximum at the upper surface. So gamma max, or the shear strain max, is given by r, is the radius, d phi by dx. Okay. Now this is your dx, right? And this part is r d phi. All right. So this becomes gamma max, becomes d phi by dx into r. R is the radius. Now look at this cross section. So the shear strain at the upper surface is the maximum shear strain, and that is given by r d phi by dx. Now what about shear strain in the inner layers? Because inner layers will not have same deformation or same shift as the inner outer layer, right? Because the inner layer, if you can see, if this is your outer layer which has gone deformed by n dash, right? The inner layer will have lesser deformation, right? Lesser shift. This is the higher shift. This is a lesser shift, and the shift will be 0 at the center point, because center point is not undergoing any twist because it's a line, right? So it remains in the same position because of the symmetry, and therefore it's going to be a lesser value. So how are we going to find it out? Very simple. The ratio of these two is ratio of their radius, right? Distance. Therefore, you can find n dash equal to r d phi, that is the maximum, and n1 dash is the rho d phi, where rho is this distance, positional distance, radial positional distance. Okay. All right. So the shear strain anywhere in between, if you want to calculate, that's going to be gamma equal to rho d phi by dx. So instead of r, it will be rho because we are looking at some layer inside. So this is your maximum shear strain, and this is the shear strain in the internal layer. So the diameter, so the radius of the internal layer from the center is rho, and that's the maximum value r. So it becomes rho d phi by dx. Okay. So for a constant phi, you will get rho equal to p rho L by phi. And this is a formula that you get. It's an interesting formula that gamma by rho is equal to phi by L. All right. So gamma by R, you have to find out from this. So that will be gamma max by R. Okay. Now that is for a solid section. What will happen for a hollow section? So the hollow section will follow similar thing that a solid section has followed. Now for a solid section, I'll say that at the point where it is starting, the center point of the circle is zero strain, as we discussed, right? This is zero strain because this does not have any speciality, in the sense this does not have any uh, inclination towards any other point. Right? So this is a symmetric point, so it cannot deform either this direction or this direction or this direction or this direction. It has to be at the center because of the symmetry, and it is maximum here at the boundary, right? Shear strain, and the shear strain, as you can see here, is a function of rho by r, right? So it goes linearly as rho changes. Okay, so shear strain is a linear function of rho. So therefore, as rho increases, it increases slowly. So maximum will be at the boundary and zero at the center. Same thing going to happen for a hollow cross section also. For a hollow cross section, the center will be zero, and then it will linearly increase, right? So the inner layer will have existing strain, and then there will be some strain, and the maximum will be at the outer layer. So there will be minimum at the inner layer and maximum at the outer layer. So remember that this is not zero at this point. It doesn't start like this. It starts zero at the center and go like that. So there will be a shear stress available at the center. Okay. Now, how do you see the shear stress distribution? That was your shear strain distribution, right? How do you see shear stress distribution? Now, shear stress distribution is easy from shear strain distribution. If you know shear strain distribution, shear stress is calculated by just multiplying it with the shear modulus within Hooke's law. So we are within a proportionality limit within. Okay, so in that case, our shear stress is given by just multiplying with a constant g. Now gamma is given as rho d phi by dx, so it becomes g rho d phi by dx. Now where is the maximum shear stress going to happen? Maximum shear stress will happen where there is a maximum shear strain. The maximum shear strain is at the boundary, so therefore maximum shear stress is going to be also at the boundary. Where is zero shear strain? The zero shear strain is at the center, therefore zero shear stress is also going to be at the center, and it will linearly increase. Okay, right? So at any location which is rho from the center, it is going to be g rho d phi by dx, and tau max is going to be g rho d phi by dx is theta, so it becomes theta. Okay, so this is a relationship that is very important for us to remember. Tau max by r is equal to tau by rho. Okay, so same thing, you can write tau max by tau is equal to r by rho. Okay, all right. Now let's relate it with, so we want to, so final objective of the part is, as I said, to relate force with deformation, right? So here also relate torque twist. Now what is the torque given to a material? Now if I give a torque on the material, what is the total, the total area will resist the same torque, right? If the external torque is T, that is going to be resisted by the full cross section, right? So let us take a small area here, and let's say that the shear stress along that area is T, is small, tau, okay? And that is at a distance of rho. So your total is going to be So the moment resisted by this small element is going to be tau into rho, right? dA. Tau dA is the force, and into rho is the moment, right? So now integral of that moment is going to give me the total moment that is resisted, or the total torque that is resisted. So capital T is given by over the area dm. All right, so that comes out to be, now we know what is tau. Tau is rho, tau max by r into rho, right? That is what I wrote here. Tau is equal to tau max into rho by r. Okay, so I can replace that with this, and that comes out to be tau max by r. So there is another rho here, so that rho and this rho will multiply and become rho squared dA. Now what is integral over the area rho squared dA? It's the polar moment of area, right? So polar moment of area is j, we write it as j, so it becomes T by j is equal to tau max by r, and which is equal to tau by rho. We wrote it here, tau max by r. Tau max by r is tau by rho, so I can write this as tau by rho. So once I know T and I know j, I can find tau at any location within the material, okay, because that will be rho known to me. So if I know the external torque applied, if I know the cross-sectional j, or moment of area, polar moment of area, I can easily find stress within the material given the location of the position where I'm finding the stress. Okay, for a circular member, since we are dealing with circular members, j is given by pi by 32 d4. And for hollow sections also, you know that this is going to be pi by 32 d outer 4 minus d inner 4. Okay, all right, now let us see how we can relate T. Our objective is to relate T with twist phi, right? So that is what we have to do. Now come here. If you come from here to here, T is given by integral over the area g rho square d phi by dx. Okay, how is this coming? This coming from the relationship that we know tau max or tau both are known to me in terms of g and d phi by dx. So where is that? This is here, right? Tau is equal to g rho d phi by dx. So this tau I can put g rho d phi by dx and integral over dA. Once I do that, once I replace that, I can understand that d phi by dx is a constant. Okay, for a given torque, d phi by dx is a constant because that's the gamma strain. So that comes out, that's not a function of area, so it comes out of integral, and then you can do the integral, right? So this g will also come out, so it becomes rho square, so it becomes gj d phi by dx. So this is for constant j. This is your torque with twist relation. So that's how you write it. D phi by dx is equal to T by Gj. Now, if you have a constant phi over a length of x, okay, then it becomes TL by Gj here over the length of L, or else you have to integrate it between phi 1 and phi 2. That becomes phi 1 to d phi, which is x1 and x2 T by Gj. So if you have multiple cross sections, okay, of different j, then this formula, that is what you have to use. But if you have a constant cross section, then you can use this formula directly. Okay. Statically determinate problems. Okay, so we are looking into statically determinate problems. Okay, the formulas that we learned is shear stress tau is T rho by J, okay, with tau max being rho max, which is your radius of the cross section. Angular twist d phi is given as integral from x1 to x2 T by Gj dx, right? And if T, G and J are constant, then phi is equal to TL by Gj. Okay, so if there are no other torque applying T1, T2, T3, or there are no cross-sectional change, so J1, J2, J3 is not there, or there is no different materials that are added up, so G1, G2, G3 is also not there. If everything is constant, for example, a simple shaft with a single torque T, in that case, it is TL by Gj. Okay. Apart from that, we learned few relationships. These are called, torque twist relations or torsion formulas. Tau by T, so internal stress by total torque given externally is rho by J. Similarly, gamma strain by rho is equal to phi twist by L. same tau is equal to G into gamma. And if you combine this relationship, you get those formulas that we have learned from this. So it comes from the same thing. Now let's look at the first problem. What is this first problem telling? First problem is stated is, this is a solid circular bar made up of steel. So this is a solid circular bar made up of steel and has a cross-sectional diameter of 2.5 centimeter. Okay, so cross-sectional diameter D is given to me. The length is 25 centimeter. Length is also given to me, L. The shear modulus G is given, 78 GPa, and the bar is subject to torque T acting at the end. So there is only one torque that is applying, that is T. Okay, what we have to find is, if the torque have a magnitude of 200 Newton meter, so T is 200 Newton meter, then what is the maximum shear stress in the bar? What is the angle of twist between the ends? So we have to find angle of twist is phi. We have to find phi, and what is the maximum shear stress is tau max. We have to find, right? So if you go back to our formulas, tau max is shear stress maximum is T is the external torque into R by J. Now diameter is given, so I can find J. R is given, diameter is given, so radius can be found out, and T external torque 200 is given. So tau max is easy to find. So tau max is going to be T rho by J with rho equal to R, right? So tau max is going to be TR by J, and if you put that values there, you get tau max. Okay, you can find it out yourself. So this is the values. You have to find J and put it. Now what about phi? Now I can use this formula only when, as I said, only when there is only one torque applying, there is no change in cross section, and G is same. So all these are applicable for this, right? This is a single material body, so G is same. There is no cross sectional change anywhere, so J is same, and there is only one torque that is applying here, right? T. Okay, not that way, this way. T. So I can use this formula, phi equal to TL by GJ. So if I put phi is equal to T is this, L is this, GJ. Remember that all units should be in a uniform format. So if you are using meter, then everybody has to be in meter. If you are using centimeter, everyone has to be in centimeter, right? And if you are using Newton, then everybody has to be in Newton, right? So you follow that for, and then you get phi. Now, second question is, if the allowable shear stress is 40 MPa and allowable angle of twist is 2.5 degree, what is the maximum permissible torque? So this is a design problem. Okay, you have been given the maximum stress capacity and maximum deformation that is allowed, that maximum twist that is allowed. You need to find the maximum torque that you can give to the material so that you are within the limits. Fine. So first is you can check these values are within the limit or not. Okay, if you check it, that's fine. Okay, I have found the J also here. J is also given here. So you have to just put it back to find the formula solution. Okay, so to do that, first is what you have to do is you have to draw a torque diagram. What is the torque diagram here? There's only one torque applying, right? So internal torque diagram is going to be the same. T, internal external load, the same here. So that's your internal torque diagram. Positive or negative, you can find out. So this is coming out of the member, so it's going to be positive, right? Both sides it is coming out of the member, so it's all through is a positive. Now, how is the twist going to happen? Twist, one side you have to assume zero twist, the other side will keep on increasing and go to a maximum value at one end. Okay, so now tau max is given as TR by J, which should be lesser than tau allowable, right? So here I don't know capital T, but I know tau allowable, right? So I can find this out. So capital T is going to be tau allowable into J by R. So you can just put those values and you can multiply and you'll get some value here, right? So you know how to find that. Similarly, phi at one end, I don't know. I have to find that. It is going to be TL by GJ, right? And then I don't know what T to use here, right? Because T is unknown to me. I have to find that T. So what I'll do is I'll recommend T is equal to phi GJ by L. Now this phi maximum value is known to me. It's 2.5 degree. So convert it into radians and put that value here. Once you do that, you get maximum T here. So this T is maximum from the stress and this T is maximum from phi. Whichever is the lower minimum of these two is my design torque. Because I cannot go more than that. If I use, the non-minimum, if I use the maximum, the value, then it will fail in, so let's say tau, T tau, that means maximum T from shear stress is higher than maximum T from phi, right? And if I use maximum T from shear stress, then the member will have more than 2.5 degree as it twists and it will fail there, right? So we have to use the minimum value, and this is the minimum value. So that's how you can solve this problem. It's not difficult. Please go ahead and do it. Yes, any questions?
A small doubt, sir. Sir, here in this rod, we apply torque on both sides, no, sir?
No, you can assume, yeah, you can assume it to be fixed at one end and torque is applied at the other end, right? So if you draw a free body diagram, it will be this.
Okay, sir. But okay, sir. Because I had a doubt in the stress diagram graphs. Like I thought it starts from the negative side and it will go to the positive side. Like
No.
Sir.
See, both side is outside is positive. As I said, any cross section you take, the outside torques are positive. Okay, torque that is going out is positive. What you are telling is then in this case it has to be like this. Then the diagram would have been something like that. You had to apply some other torque here somewhere.
Okay, so basically we fix a reference here and then start from zero, right?
Yes, so you fix it. So you assume this to be fixed, because that will give you same free body diagram, right?
Yes, sir.
Okay. Now let's look at variable cross section. What happens? So we all know that we have found it for axial members. So for torque, it is going to be same relation. So you have to always draw internal torque diagrams. Once you have drawn the internal torque diagrams, it's very easy for you to solve. So these TCDs are internal torque diagrams. They are internal torques, and then you can add them up as I have shown in the earlier page. That all phi's should be added up, and these are all internal torques. Remember that. Okay, so I'll write that here. TIs are internal torque. TI bar okay. Now, as in axial members, we said that there is something called stiffness and something called flexibility, which we can find from the formula. Here also we can find it. We call GIJI as torsional rigidity. For example, AE is called axial rigidity, right? And torsional stiffness is GJ by L and axial stiffness by AE by L. You can see the complete relationship. The material parameters, the geometric parameters divided by length. Here also the material parameter with the geometric parameter gives you torsional rigidity or axial rigidity. Okay. In case of continuously changing cross section, what did we do for axial members? We just integrated it. Here also phi is, you have to integrate 0 to L d phi, and d phi is going to be tau dx by gj. Okay, just integrate it. That's all. And if you have distributed torque all through, then the torque is also a function of x, that also gets inside. So apart from very simple ones where the cross sections are not changing continuously, there is this only tapered cross section, step cross sections, or there is only step change in material or j diameter, then only you can use the summation rule. But if there is continuous change of anything, either torque or cross section or the material, then you have to use this formula, integral. Okay, let's look at this problem. Problem 2. What is it telling? Okay, there are two torques that are applied here. So this is the member, okay, and it is fixed here at C point. There is one torque going outside the member applied at D, and there is another torque going inside the member at L at some point. The length from the support is L1, that one, and this is L2. Okay. Now we have to draw the internal torque diagrams, right? So if I take a cross section here, AA, what is going to be the internal torque diagram? This is my AA cross section. Internal torque, this is outside T, right? Going out of T, and therefore this is a positive T that is going to apply here. Okay, so this is a positive T. Now come to this, after this, take up cross section here at BB. So at BB cross section, you have T acting this side and T by 2 acting this side. So what are we going to have? You will have effectively T by 2 acting outside, right? So again, in this cross section, you have something applied on the outside. So it's also positive. So it's going to be t by 2 positive. All right. There is a jump here. Remember that wherever there is a jump, there has to be a load that is acting there. Whether it's an axial member, whether it's a torsional member, or it's a beam, anywhere. If there is a jump, the jump should be contributed by a force acting there. So there is a torque T by 2 is acting here, and this jump, shortening or the jump is also that T by 2, the same T by 2. Now phi is going to be summation of this phi and that phi, right? So this phi is going to be T into L by 2 by Gj, right? Same thing, Gj, same value. And this one is going to be T into L1. So phi 1 is going to be T into L by L1, T by 2 into L1 by Gj, right? So you add them up, so you get your total phi. Okay, so when you draw the torque diagram, twist diagram, it's going to be 0 here, and it will grow like this because it's a function of L1, so it's a function of x here. So it's going to go like that, and then there will be a slope change because this added up with this at this end. So it's going to, there is to be a slope change here like this. So that slope change is contributed or attributed due to the load that is acting here, the torque or twist that is acting here. Okay, fine. So whenever there is a load or there is an external moment that is applied there, or external torque that is applied there, there will be a change in twist diagram, right? There will be change in internal torque diagram. Similarly, there will be change in bending moment diagram or bending shear force diagram, as well as there will be change in axial, internal axial force diagram. Okay. These are the things that you have to remember to cross-check your solutions. Okay, here is another problem, which is of a continuous change in cross-section, right? From A to B. So at A, the diameter is dA, at B, the diameter is dB. And I'm using only one single torque applied there, right? So you can assume that one of the side is fixed, right? So it's a free body diagram of that member. So this T and that T is same. Okay. J you can find, J will be a function of the diameter, and the diameter is continuously changing. So J is a function of X, right? What we have to do is we have to determine the maximum shear stress in the bar and the formula for angle of twist. Now, where will be the maximum shear stress? The maximum shear stress will be at a location where there is a minimum area, right? Because the same torque is applying. So where there is a minimum diameter, the stress will be maximum there. Okay, so let's see that. T by J is tau max by R, and I have to find tau max, right? I know T, I know. So this R and J will make sure where is your tau is max, because R and J both are changing with time, right? So we can write that tau x is equal to T into Rx by Jx. Now what is Rx? Rx is dx by 2, and Jx is pi by 32 dx4, right? So this dx will cancel, and it will come out to be T by D. Now it has to be minimum at this section because it's a function in inverse function of D, right? Inverse function of D cube, and therefore it has to be wherever D is minimum, stress is going to be maximum. So at A it's going to be maximum, so it's going to be 16T by pi D cube. Okay. Diameter at any distance from D is given by this formula. So you can put that formula back here and find the solution. I find the torque at any location that you want. Now angle of twist. Now the torque T is constant, but J is a function of X. So you have to use the integral formula as we discussed. So 0 to L T dx by Gjx. Now Jx will depend on dx. This is your dx. And you can put that formula back here. And you just have to integrate, that's all. And once you integrate, you get phi. That's the formula for phi that you get. Okay, with that, I'll stop now. I have given another problem here that you have to solve yourself. Please solve it yourself. Okay, where this change in radius is given by a formula k e to the power of minus alpha x. So here the change in radius was linear, right? It was a linear, right? It's a function of only x. Now it's not a function of x, it's a function of e to the power of minus alpha x. So you have to do the same thing, just you have to put this formula within the integral sign and get the integration done. With that, I'll stop. Tomorrow we are going to take indeterminate problems.